A wide variety of processes of importance in the chemical process industries involve the transport of ionic species in bulk electrolyte liquid mixtures within charged particles, such as ion exchange resins, and across charged membranes. Examples include electrolysis, electrodialysis, ion exchange, metals extraction, and fuel cells. The objective of my presentation is to highlight some key and important features of ion transport that is of relevance in these processes. In particular, I underscore the importance of the term that I call the electrostatic leash in determining the ionic fluxes. For background theory, consult two of my publications that are shown here. Also, watch my video presentation titled Uphill Diffusion on my YouTube channel. The transport of any ionic species I is described by the set of Nernst-Planck equations named after Walter Nernst and Max Planck, who got the Nobel Prize respectively for chemistry in 1920 and physics in 1918. The Nernst-Planck equation writes the ionic flux of species I as a sum of two contributions. The first contribution is due to the concentration gradients, but C is the molar concentration, and DIW is the ionic diffusivity. W stands for water, I is the ionic species. In addition, there is a term that describes the influence of the electrostatic potential gradient. F is the Faraday constant, R is the gas constant, T is the temperature, and Z is the charge on the ionic species I, and Ci is the molar concentration of species I. We note that for positive ions, Z is positive, and for anions, Z is negative. Therefore, the second contribution, which I termed the electrostatic leash, is either positive or negative depending on the species charges. Unless you consider a process in which you draw current, such as in batteries or fuel cells, the constraint of electro-neutrality holds, which means that the mole fraction times the charges of species summed over all the ionic species is 0. The Nernst-Planck equations are valid for dilute electrolyte solutions in which the activity coefficients of each of the ionic species is unity, and there are negligible ion-ion interactions. For concentrated ionic solutions, we need to adopt a more general approach to describe the fluxes of the ionic species, and this is discussed in my presentation entitled Uphill Diffusion, that is available on my YouTube channel. Let us now highlight the consequences of this contribution of the electrostatic leash in a variety of scenarios that are important to the chemical process industries. In 1941, Winograd and McBain published a set of experimental data on effective ionic diffusivities that were measured in a two-compartment diffusion cell shown schematically here. The two cells are well mixed. The top compartment contains a mixture of hydrogen chloride and barium chloride, and the bottom cell is pure water. The two cells are separated by a sintered glass disc that is very thin. Since the two compartments are well mixed, the concentration gradients of each of the ionic species are restricted to this thickness of the porous diaphragm that separates the two cells. The measured ionic diffusivities of hydrogen, shown by the red circles, chloride ions, shown by the green squares, and barium, shown by the blue triangles, are plotted as a function of the square root of the ratio of the concentration of hydrogen chloride and barium chloride in the top compartment. The ionic diffusivities at vanishingly low concentrations of the electrolytes are as follows. Hydrogen has an ionic diffusivity that is about a factor 10 higher than that of chloride and barium. But we note that as the ratio of the concentration of hydrogen chloride to barium chloride is increased, the ionic diffusivities that are determined in the experiments is significantly lowered. Concomitantly, we note that the ionic diffusivity of the chloride ion increases, whereas the ionic diffusivity of the positively charged barium, that is much tardier than H+, is further reduced to a value that is practically 0. The explanation of the reduction in the ionic diffusivity of H+ and of barium 2+, and the increase of chloride that is negatively charged is to be found in the influence of the electrostatic leash. Now, hydrogen is the most mobile of the three ionic species, and due to its high mobility, it enters the bottom compartment at a very fast rate, creating a charge imbalance there is an excess of positive charge here that has the effect of accelerating the motion of the chloride ion in order to maintain electroneutrality in the bottom compartment. A further consequence of the charge imbalance that is engendered by the fast diffusing H plus ion is that the tardier barium 2 plus ion is further reduced in its mobility because of the excess of positive charge in the bottom cell. So the electrostatic leash acts in different ways on the positive ions and the negative ions. The positive ions are hindered in their transport, whereas the negative ion, chloride in this case, is accelerated in order to maintain electroneutrality. Yang and Pintaro report a set of experiments on ion transport across a cation exchange membrane that is made of naphion. The left compartment contains salt solutions containing sodium sulfate and cesium sulfate. The right compartment contains sulfuric acid. The molar concentration of sodium sulfate in the left compartment is the same as the molar concentration of sulfuric acid in the right compartment. The concentration of cesium sulfate is significantly lower than that of sodium sulfate. The cation exchange membrane prevents the intermembrane transport of the sulfate anions and only allows the cations of sodium, cesium, and hydrogen to be transported. The experimental data on the uptake of cesium and sodium ions in the right compartment are shown by the blue circles and green squares, and the red triangles show the uptake of hydrogen ions into the left compartment. Remarkably, we note that the cesium uptake into the right compartment exhibits an overshoot in its concentration as it equilibrates to its final steady state value. The transport of cesium uphill and the occurrence of transient overshoots are quantitatively described by the model that incorporates the Nernst-Planck equation for describing the ionic fluxes, and these are shown by the continuous lines in this diagram. The physical explanation of the uphill transport of cesium is as follows. Hydrogen ion has a very high diffusivity, about a factor 5 higher than that of say sodium and cesium, and it gets transported very quickly into the left compartment, creating a charge imbalance, and therefore to maintain electroneutrality, that enhances the transport of cesium across the membrane into the right compartment. And for a brief period of time, the concentrations in the right compartment are higher than the final equilibrated values. Yoshida and Kataoka report experiments for transient uptake of cations in a cation exchange particle τx50 wx10. The cation exchange particle consists of fixed negative charges, and negatively charged anions cannot enter the particle. In one set of experiments, the ion exchange particle is loaded with sodium ions, and the bulk solution surrounding the particle contains a mixture of nitric acid and zinc nitrate. The transient uptake of hydrogen and zinc into the particle and egress of sodium cations from the particle are monitored in the experiments. The uptake of the hydrogen ions are indicated by the red circles. The uptake of the zinc cations is indicated here by the blue triangles, and the egress of sodium cations is indicated by the green squares. We note that the experimental data show an overshoot in the ion fraction of H plus before it equilibrates to a value of 0.5. The continuous solid lines are the simulations of the transient uptake using the Nernst-Planck equations for describing the ionic fluxes. The explanation in simple physical terms for the overshoot of H plus is as follows. The ionic diffusivity of H plus is about 1 to 2 orders of magnitude higher than that of sodium and zinc inside the ion exchange particle. Consequently, the ingress of H plus into the particle occurs at a faster rate than the ingress of the zinc cations and the egress of the sodium cations. The fast ingress of the hydrogen ions into the particle causes a charge imbalance that has the effect of slowing down the ingress of the zinc cations and speeding up the egress of the sodium cations. The net result is an overshoot in H plus, and you will note that there is a concomitant rapid decline in the ion fractions of the sodium cations, shown in green. In a different set of experiments reported by Yoshida and Kataoka, the cation exchange particle is initially loaded with H plus and the zinc 2 plus cations, and the surrounding bulk liquid mixture is a solution of sodium nitrate. The transient development of the ion fractions of sodium, zinc, and hydrogen cations are shown here in using symbols. The continuous solid lines are the simulations of the transient uptake using the Nernst-Planck equation to describe the ionic fluxes. The egress of H plus is very quick, and this enhances the flux of sodium into the particle, while the egress of zinc cations is slowed down. No overshoots or undershoots are experienced in this case. The transient equilibration trajectories followed by the three cations in the two experiments shown in the previous two slides are plotted in ternary composition space in this figure. It is noteworthy that the trajectory followed here, shown in blue, when the ion exchange particle is initially loaded with sodium, is exhibiting an overshoot in H plus, whereas the reverse equilibration, in which the particle is initially loaded with a mixture of zinc 2 plus and H plus, follows a completely different path that is not symmetric with the blue path. In the red path, no overshoot or undershoot in H plus is recorded. This underscores the asymmetry that is inherently present in ternary ion exchange processes. This asymmetry is adequately captured by the Nernst-Planck equations. The takeaways from this presentation are summarized in the slide. The electro-neutrality constraint engenders important consequences for ionic diffusion. Three consequences are listed here. Ions are either speeded up or retarded depending on the direction of ion transport in order to maintain the electro-neutrality constraint. For transient uptake of ions into charged ion exchange particles such as resins, the electrostatic leash induces asymmetry in the adsorption-desorption process, and during transient uptake it also may engender overshoots in the transport of the more mobile ions into the particle. For transient exchange across charged membranes, we may experience transient overshoots of one of the ionic species depending on the direction in which the ion is transported across the membrane. For further background details, please consult these publications listed here.